Thank you, Andre. Thanks, everybody. Um, this is the Learning Lobby and Networking session. I'm going to be doing an introduction to quantum communications. I want to thank all the sponsors and One Quantum LLC, as well as the women in Quantum who invited me to give this presentation. And I want to thank my group, the Incunet CALTECH group, the JPL collaborators in Incunet, the Fermilab collaborators and others, Launchers group at Harvard, Jaffari's group, as well as DOEHP, BES, and ASCAR that have funded a lot of the work that we have been doing on quantum networks and communications, as well as Kavli and Brinson Foundations. And I want to give a shout out to my undergraduate student, Alex, Michael Zocapa, and Ben Bartlett. Ben, I will show you some simulations of quantum communications at the end. And Ben worked on them in 2018 when he finished undergrad at Caltech and moved to do graduate school at Stanford. All right, so let me start with quantum technologies. Quantum technologies and quantum engineering is a field that is new, relatively speaking. When I was in grad school, I could not take a class on quantum devices or quantum technologies or quantum engineering. But now most of the universities have some program, and there is large programs, research programs in the national labs, as well as NSF centers that are focused on quantum information science, quantum information technologies, and engineering. And eventually this field is invading many, perhaps even most science field, once we admit that super precise measuring techniques can and do involve some sort of a quantum device and quantum measurement. Now, computation in science has proved to become a part of the scientific method. So imagine what quantum computation will do for us. And imagine if quantum computation is on the cloud, what quantum networking and quantum communications will do. In the past decade and today, quantum engineering, you can call it an applied fundamental field because there's still fundamental research involved, or a fundamental applied area where physics and in that materials, chemistry, CS, math, and many other domains melt with engineering. Now, quantum communications refers to systems and approaches enabling shuttling quantum information, including qubits, quantum bits, not zeros and ones, but qubits represent multiple combinations of zeros and ones simultaneously, as well as quantum entanglement, quantum states, and the relevant communication protocols involved. You all hear from the newspapers or science magazines or the papers that are being pushed in the past decade, a lot of work on quantum communications that involve secure protocols like quantum key distribution, protocols for secure key distribution among people who want to exchange securely information, and more robust exchange of or shuttling quantum teleportation, so various quantum teleportation protocols that involved quantum entanglement distribution. And I will talk a little bit about quantum entanglement and why we are excited about the physics also of quantum entanglement, not only as a resource or a primitive for quantum communications. I wanted to go back in history in the beginning of the century when the first quantum network and first quantum communication protocols were developed in 10 nodes across Boston and Cambridge in the collaboration between BBN, Harvard, BU Photonics, NIST, IBM, and others. And this is the original paper from the early 2000s. And to say that this is one of the nodes, it was a Bob-like node. They named it Barb, the one entanglement-based receiver in 2004. You see it in this picture here. And quantum networks, the physical layer of quantum communications is quantum networks, the implementation of the paths for quantum communications. And these involve long-distance quantum information shuttling, quantum entanglement distribution that involves a quantum cluster or a quantum cloud. Broadly speaking, the networks of networks, the network of networks is the internet today. So the quantum network of quantum networks is what we call a quantum internet, which we are doing research in order to implement. It requires end nodes where you can have processing, quantum processing, or quantum sensing, and many more devices in the middle. Some of them do not exist yet, like repeaters or quantum amplifiers for that matter, memories, quantum memories, and transducers at the edges. So the elements for quantum communications and networks is generation of quantum information, processing of quantum information, as mentioned before, so nodes, and that can be various physical layer platforms. For example, it can be ions, it can be superconducting bits, qubits, it can be atoms. There's various groups and industries that are working on the research of these various physical platforms for doing quantum computation, quantum processing, as well as photodetectors. There's media, which can be fibers or free space. There's switches for the controllers and routers of how the information, how various users are communicating. The amplifiers that we mentioned before, the quantum repeaters, based on quantum teleportation to avoid the non-cloning theory. Remember that in quantum communications, we can prepare states, but we cannot copy them. And then memories with the importance is that they have a good lifetime. In other words, they can keep the information with high fidelity for a long time. The teleportation, what we call it, the teleportation protocol is the quantum wiring between remote gates and nodes, and it requires very good entanglement sources and advanced single photon detectors, and this is an active area of research. The way we, in a cartoonish way, if we want to talk about teleportation, we have those two agents, we name them Alice and Bob. Alice wants to teleport the information from herself to Bob. So she, through entanglement, she does this by sending on the classical channel zeros and ones. And based on this information and the entanglement information, Bob can reconstruct the teleported information. This is a very cartoonish way. And if we want to show it in a manner of sort of equations, if you want, with the states, there is a transmitter and a receiver that share entangled qubits. The transmitter gets an input qubit, makes a measurement on the joint state of the input qubit and the part of the entangled qubit. And then the measurement, which results in 2 classical bits, is sent to the receiver, and that's the classical channel that we saw on the cartoon. The transformation at the receiver then yields the information on using the classical bits and the information that was sent again through the entangled qubits, the sharing of the entangled qubits. Let me say a couple of words on entanglement, a couple of physics words on entanglement. Entanglement is the quantum phenomenon in which objects become so correlated, so closely linked, entangled in English, that they share some sort of a same existence. So in physics, the way we say this is that they're described by the same wave function. Now, entangling things is not too difficult. Most subatomic interactions involve entanglement of one sort of another, but the trouble is to pin it down. So entanglement is fragile and fleeting. It leaks in the environment, and that is so why it's so difficult to preserve, to observe, and ultimately so difficult for physicists and engineers to play with. Now, in recent years, in the past, since the end of the century, let's say, the previous century and the beginning of this century, there's a lot of experiments and scientific papers where we learned how to entangle all kinds of objects in pairs, be it photons, be it electrons, atoms, and so on. So in 1999, for example, there was a Q-treat that entangled 3 photons, and then in the past 20 years, we have arrived to the point that there are experimental scientific demonstration of even entangling 8 photons, manipulating and observing them. Now, here in the cartoon, there's 2 electrons in a single spin, in a singlet spin state, the A and the B. Here, just the spin shows up and down. The total state, the pair state is at 0, and there is an observer. This is in a cartoon way. Now, the A and the B are going to be moved halfway across the universe, and the A says, "Tell me if you're up or down. I have to be the opposite." This is based on the entanglement, the fact that they share the wave function at their beginning. And the B is saying that I won't know until somebody measures me, according to Bohr. And then the A says, "Don't get so far away." We said it is going all the way half the universe. Your signal can't exceed the speed of light, according to Einstein. And B says, "Don't worry, we're both part of the same system," according to Bohr. And the observer says, "This is a large system." This cartoon is showing us that in the heart of entanglement is the notion of locality, if you want, or how we separate atomic systems. In quantum mechanics, there's no separation of the observer and the observed. They belong to the same system. The 2 electrons here and the observer are part of a single system. So you hear about the EPR experiment, the Einstein-Podolsky-Rosen experiment. It does not demonstrate an incompleteness of quantum theory, as Einstein would have said, but rather the naivete of assuming local conditions in atomic systems. Once we connect the subatomic systems and untangle them, then they never really separate. So the experimental observation of that was first done by Clauser in 1978, so the previous century, and in 1982 by Aspect. And then you have heard in the past decades in Delft, in ETH, here at CALTECH, and in many other places, we have demonstrated that. So the main point here is that despite of the appearances of phenomena, there is a foundation upon which reality rests, where it looks like we are on a network or a web, and this again is an active area of research, not only for quantum networks and communications, but in connecting them with possibly with the quantum origin of space-time. So it's used a lot in ADS-CFT correspondence with quantum information language, how the universe, essentially, how space-time, what is the origin of space-time, and I will say a word in that in a minute. I wanted to show you here our December 2020 paper, where we have demonstrated high fidelity teleportation in photonic systems. This is with this is our experiment here part of the experiment here, I should say, with Alice, Bob, and Charlie, and about 55 kilometers of spool fiber. We're developing also a hybrid system with telescopes on the top of the laboratories and a little quantum intranet, if you will, at CALTECH, so that we test memories that other collaborators are doing, and plug in other components from collaborators in the laboratories and other academic institutions that collaborate with us. This is a student of mine, Samantha Davis, showing the fidelity in a real-time system. We do synchronization and monitoring and real data taking in order to be able to do real data time analysis and figure out any problems, any losses on the fibers. And this is another student of mine, Andrew Muller, who is working on you see him on a naked fridge here, on a naked dill fridge, where we put the state-of-the-art optimized photodetectors that are fabricated at JPL and optimized across many metrics so that we improve the fidelity, the teleportation fidelity. Now, within this program, which we started in 2017, 2018, we have the Fermilab Quantum Network, the CALTECH Quantum Network. These are two sister networks. One is a commissioning network and testing, and one is a deployable one, because we have more space here at Fermilab so that we can put nodes across distances of many kilometers, and even there is a plan to go to downtown to Chicago, and we're working here again with the national laboratories, with Fermilab and Argonne, as well as partners at Northwestern and elsewhere. This is at the very beginning when we were building the network at Caltech and shipping it at Fermilab. And here again, this is a picture from our experiment at the testbed that we have at Caltech. And in fact, at the realization of the connections of QIS with a lot of fundamental science, this was a brochure from the OSTP, from the Office of Science and Technology at the White House, where it describes the promise of QIS. And as I said, the domain sciences that can take advantage of networks and communications between quantum sensors, between quantum processors, end-to-end systems of quantum sensing, quantum links, quantum processing is bound to change the world. And we do know that the physics works, and there is a lot of engineering that needs to be developed, as well as along of devices. I mentioned the hybrid systems. I wanted to mention that there is a lot of work at NASA, JPL, Lincoln Labs, MIT, in order to, and other places in the world, in order to make satellite links and do transmission of entanglement, distribution of entanglement through satellites. So you have ground stations, ground nodes, and stations in space. And along these lines, I wanted to mention that, for example, if you stretch the optical communications program that NASA has, this is from a demonstration that they had, the Deep Space Optical Communication, the technical demonstration mission. This is the longest range demonstration of free space laser communications, and it is to demonstrate optical communications from deep space. This is called the PSYCH mission, that goes all the way to 2.7 astronomical units at rates of 267 megabits per second, in order to validate the acquisition laser pointing control and show the high efficiency signaling. And you see here how many telescopes, ground telescopes, are equipped with these single photon detectors and the PSYCH spacecraft. This is to be launched as we speak, I think, and it's just a demonstration. But the future of optical communications, this is not at the single photon level yet, but you can call it like the pre-quantum or the semi-quantum type of optical communications in space, that for such long distances you will require this type of communication. All right, now besides quantum, computing, quantum communications, and I want to remind everyone that computing as we know it, the transistors, is based on quantum physics, not the physics of superposition of states, or not at the Heisenberg limit, and not entanglement, but the transistor is based on actually quantum physics. I wanted to go back to entanglement and show you a little bit from nature. This is a nice graphic that shows how physicists and quantum information scientists now are trying to recast, let's say, or find a way to describe space-time as with origins coming from quantum physics. So if we go in at the bottom of this, we will see that space-time can be described by tensor networks, and in the heart of these are the two entangled pairs. Here, for example, as we go in, we will see them wiggling, and then once we measure the one, we know the other. So we think that entanglement, the physics of entanglement, can provide the resource for us to understand the origins of space-time. With this, I want to stop it here because I don't have much more time, but I wanted to show you a couple of examples. Let's see. This is from, I didn't put the link of that, but this is from the internship of Bartlett, my student from 2018. He had an InQNet internship in the summer before he went to grad school. And so here is a demonstration of quantum teleportation, where Alice, this is the protocol described in a quantum circuit, but the process of the quantum teleportation protocol allows two parties to share the entangled pair, as we described in words, and to transfer an arbitrary quantum state using classical information. And so if we run it, and I will do it, let's see, I ran it just before, so I will put this in the link on the slides that I will submit so people can run it. This is public code, and there is an associated paper with that gives a lot of the information about some quantum communication protocols. So it runs as a Jupyter notebook, and it explains how Alice, the agent Alice, generates the entangled parties, how she entangles her qubit with the joint entangled qubit that will be used for Bob to decode the information, her measurement, and then what Bob does, the operation that Bob does in order to recover the information that Alice gave him. So if you run this, you get agent Alice, agent Bob receives qubits from Alice, and then the simple demonstration is saying, here's the teleported states, here's the received states. And if you look at the end, as they are transmitting the information, what you observe and what you expect is very similar when you start rotating the various states in order to do a test with manipulation of the states. There's one more that I want to show because it's fun. If we put the eavesdropper, since baked in the quantum entanglement distribution is security. Here, for example, we take it's a man in the middle attack demonstration, but it's really a woman in the middle attack demonstration. It's Eve. And we have agent Charlie, who will distribute the pairs, the bell pairs, the entangled pairs between Alice and Bob. Alice will send information to Bob with via superdense coding, and then Bob and Alice's transmission Bob receives Alice's transmission and decodes the information, and reconstructs rather the information. Now Eve tries to intercept Alice's message, and if we run the simulation here, and I ran it earlier because it takes a little bit of runtime, you get in the end. The transmission of Alice was an image in a bitmap format. That is what Alice sent, this InQNet image. You see Bob and Eve intercepted it. Bob's image is noisy because Eve intercepted, and so however Bob can in various ways can still reconstruct the message, but what Bob knows here, because it's so noisy, is that somebody intercepted. And Eve's image is just pure noise. It's just random noise. So Eve, in her way of trying to disrupt the quantum communication, she just got noise. And this is one of the sort of easy ways to understand how security is baked in quantum entanglement, teleportation, quantum communication protocols. There's a few others here. I will just show you which others they are. There's the quantum error correction, where there is a dumb Alice and a dumb Bob, and an Alice and a Bob that perform some error correction using Peter Shor's code. In the end, the Alice and Bob, the dumb Alice sent the message which said Peter Shor once lived in Rodek 238. This is one of the Caltech undergraduate housings, but who was the airman? And dumb Alice did not error correct her message. That means that the simulation had various sources of noise, and dumb Bob received this gibberish here. The smart Alice that applied Shor's algorithm sent Peter Shor once lived in Rodok 238, but who was the airman? And Bob received exactly that. These are the clever Bob and the clever Alice that applied Shor's algorithm in order to get the correct message. With that, I think I wanted just to share this link here for the quantum source of spacetime. Physicists are very excited about that, and we can take the two black holes being entangled through a teleportation protocol, a wormhole, a communication between black holes, or the black holes can be quantum computers, but the physics of entanglement there is extremely important. And one can even, if you look at the byline here, is that the entanglement is necessary for space to exist in this kind of thinking. So with that, I close, and because I'm an Ian Banks fanatic, I wanted to mention that in one of his books, he said, "We are information, ladies and gentlemen, but we are lucky enough to be encoded in matter itself." And I would say we are quantum information, in fact. And with this, I stop. Thank you.